Chapter 5, Problem 50. We're told that there are two satellites orbiting the Earth at altitudes of 7,500 kilometers and 15,000 kilometers above the Earth's surface. Which satellite is faster and by what factor? So let's go ahead and draw a picture and probably point out that although satellite orbits don't have to be circular, let's make that assumption because it'll certainly make our lives easier. So we have the Earth. Let's put the Earth here. That is a nice looking Earth. E for Earth. And the orbit of one satellite will indicate like this, and the orbit of another one like so. Of course not drawn to scale. Let's denote this radius as R1. You notice I'm drawing this to the center of the Earth because that's what matters for figuring out what the force of gravity is in Newton's universal law of gravitation. This will be R2. Okay, let's go ahead and write down what do we want. We want which one is faster and by how much. So really what we want is something like the ratio of, let's say, V1 over V2 or V2 over V1, and from that we can figure out then which one is faster. All right, conceptually, what might we need? Concepts. We've got stuff going around in circles, so we've got uniform circular motion. At least that's a good approximation to make to start. We have the force of gravity, so we have gravitation. And when we have forces, we have Newton's second law, and that should be good enough to get going. All right, we have a picture, we have what we want, concepts. What we have known, let's go ahead and write down the knowns. We're not told what the masses of any of the satellites are. Hopefully we don't need them. We do know G, and we can look up the mass of the Earth, and we can look up the radius of the Earth. We know that R1 is the distance of 7,500 kilometers, that's measured from the surface of the Earth, plus the radius of the Earth. So an easy mistake to make is to forget to include the radius of the Earth in that number. R2 is then the radius of the Earth plus 15,000 kilometers. We want to get speeds, so we're keeping that in the back of our head. Uniform circular motion, what equations might be associated with that? Well, there's really the main one. The acceleration that's centripetal is related to the speed and the radius. Okay, the law of gravitation, that tells you the force of gravity, its magnitude anyway, involves two masses. G, the mass of, we're going to be interested in the gravitational attraction between the Earth and one of the satellites. I'll just generically write that as little m. We can put M1 or M2 later on to indicate satellite 1 or satellite 2, and divided by whatever distance you have squared. So that's the force of gravity. Uniform circular motion, Newton's second law, that tells us that the net force is equal to mass times acceleration. So let's make some progress and see if we can figure out how the speeds might come into this. If we combine all three of these, Newton's second law says the only force acting on any one of the satellites is the force of gravity, Gm over r squared, is equal to ma. Well, it's the mass of whatever satellite you're talking about. So you see right away that the mass appears on both sides of the equation. The acceleration is centripetal, so that's v squared over r. The masses cancel, and you can multiply by r. And so we end up with a sort of master equation that Gme over r is equal to v squared for any satellite at any distance, as long as it's going around in a circle. So this is what we're going to use. In fact, this allows us to figure out right away what makes v bigger. Well, that happens when r is smaller, because when you divide by a small number, you get a big number. So right away we know that R1 is smaller than R2, therefore the speed of the satellite that's closer to the Earth should be going faster. Now what we want to do is actually get the numerical value. What is V1 over V2? Let's do that. And by waiting to put in numbers, we're actually going to save ourselves some trouble. V1 over V2. Let's only put in numbers at the very end. V1 over V2 using this master equation, which, by the way, simplify this a little bit. This tells us that the square root of Gme over r is equal to V. So V1 is GME over R1, I'm using this equation for satellite 1, square rooted, divided by the same thing, but using R2. See that the G and the ME are common to both the top and the bottom, and so they don't matter. The G cancels with the G, the M cancels with the M. This R2 is in the denominator of the denominator, and so this should simplify to be the square root of R2 over R1. Keeping track of, we're expecting this number, this ratio, to be a number bigger than 1. Is R2 bigger than R1? Yes. And so finally what we can do is plug in the values we have. I'm going to go ahead and remind you that the radius of the Earth is approximately 6,370 or so. I think Google says 71. The precise digit doesn't matter too much. When we plug in all the numbers, we find that this ratio is about 1.2. In other words, V1 is approximately 1.2 times bigger than V2. And that's our final answer.